Today on By the Book Science Edition, From Art to Modern Science, Understanding Waves and Turbulence.
Throughout history, humans have marveled and thrilled at the waves, breakers, eddies, vortices, and turbulence that occurs in fluids such as the water in oceans and streams. Artists from Leonardo da Vinci and the Japanese Katsushika Hokusai and Hiroshige Anders, through Winslow Homer and Vincent van Gogh, to Morris Graves, Jackson Pollock, and Ned Kahn, have graphically portrayed the properties of waves and vortices. Many scientists have observed and studied the properties of waves and turbulent behavior, and slowly mathematicians have developed mathematical theories to describe and simulate these properties. From the 17th century through the middle of the 20th century, theorists such as Euler, Navier, Stokes, Poisson, Korteweg, de Vries, Reynolds, Prandtl, and Taylor developed this modern theory. However, most of their equations have proven intractable to solve by standard mathematical analytical methods. But the rapid development of the modern computer and its application by pioneers such as John von Neumann has broken this deadlock. So it has been possible for modern scientists such as Norman Zabusky, the State of New Jersey Professor of Computational Fluid Dynamics and Jacobs Professor of Applied Physics in the Department of Mechanical and Aerospace Engineering and the Cape Center here at Rutgers University, who's our guest today, to visualize, quantify, and characterize the important features of waves, vortices, and other excitations in fluid simulations. Indeed, these simulations and visualizations are the major tool of fluid dynamicists today. Hello, I'm Paul Leath, and welcome to Science Edition. And welcome, Norman. We're glad to have you on the program today.
Thanks, Paul. Thanks for inviting me and giving me a chance to express all these things that we're going to talk about.
Okay, well, let me begin by asking you, just to start, what are the different kinds of waves that exist in fluids?
Well, when you talk about waves, you talk about the physical environment, for example, and another aspect which I'll come to. But the physical environment, for example, is like a wave at an interface, like an air-water interface. For example...
So on the surface of water.
Yes, right. So this is a carefully controlled laboratory experiment where a large drop falls in the water, something we're all familiar with throwing stones in ponds. And what comes out is a series of ripples. Those are low amplitude...
circle is a wave that travels outward with a speed, I presume, that depends upon the water in some way.
Yeah, it depends on whether it's a deep water wave or a shallow water wave.
Okay. And what other kinds of waves are there?
Okay, so then there are acoustic waves by which we speak with each other.
Oh, of course.
Okay, right. And where you hear music or sound or any kind of thing, even in solids. And finally,
so that's a disturbance that travels through the air, through the gas particles that make up the air.
The gas particles, right, exactly. In other words, there's usually some underlying carrier depending on the medium. And the most common, a very common wave that we all experience is electromagnetic waves, light and X-rays. X-rays which exist in the cosmos as well as are harnessed for medical applications.
And those are oscillations of electric fields.
That's right. Electric and magnetic fields are oscillating.
Fields, right.
Right. And they travel at the speed of light, so-called. All those different waves.
Different kinds of waves. Well, what are the properties of these waves?
Okay, so I mentioned the speed. Now, the speed is a fundamental property of all waves. And for example, in air, it depends on the so-called speed of sound, which is based on the temperature. For a water wave, for example, like that little ripple, it would depend on the wavelength and, say, the height of the channel, if it's a shallow water wave, from the top to the bottom. And so we talk about the frequency of a wave and its wavelength. Okay, so the
wavelength is what, the distance between crests or something?
That's right. So the characterization of the wave is say from one crest to the other crest, or one trough to the other trough.
Okay.
You think of like a little oscillation.
Okay.
And the frequency would be the frequency times the wavelength is the speed of sound. So if you're given two, you get the other. Okay. And we talk about infrared, ultraviolet. Those are different wavelengths.
Those are just different wavelengths
of the same light. Yes.
Basically light. Yes.
Right.
Okay.
And one other characteristic which I wanted to come to was the amplitude of a wave. Okay. And most of the things I just talked about were small amplitude waves. Now, if you put a lot of energy into a wave, and this you can do in many different ways, like an explosion, or So,
or what, a breaker or something?
A breaker, for example.
Hitting the beach.
That's right.
Yeah.
So, for example, the tidal force causes waves to come into a beach, and if the inclination is sufficient, the wave will
in the picture here.
Yes, right. In this picture here, you're seeing the wave after it has steepened and turned over. So you see a plunging breaker of a wave, and that's called a tunnel that surfers use. This is by Brian Bielfield, a surfer photographer.
And so this happens when the amplitude gets very big and perhaps nonlinearities and other things actually come in.
Thanks for saying that. I meant to say that. So most physicists analyze small amplitude wave phenomena, but engineers and the people who are concerned with large energy will analyze waves that are much bigger and become nonlinear and form shock waves, actually. And so shock wave is a manifestation of a strong nonlinear wave.
So it's been a problem over the years describing accurately all of these various properties, I suppose, of these various kinds of waves. Well, I guess that began with artists over the years trying to picture these various properties of waves. Has there been a lot of that in the art world?
Well, I'm sure artists in antiquity tried to render these things, but the first artist, scientist, and engineer, the great Leonardo da Vinci, actually spent a lot of his time sketching waves. There he is on the left, and you see a pole immersed in a stream. And what is happening is there is a region in front of the pole, which is actually a vortex, which we'll come to, and behind it is a wake, that stuff, turbulent wake, which we'll also come to.
Right.
And
those are actually Leonardo's drawings, actually.
That's right.
Right.
They are from his Codex pictures. But one thing I want to point out that I collected on this photograph was not only was he interested in actual practical situations for which he was hired to do something, but he also realized that there were very fundamental configurations, and they are seen at the bottom there.
On the bottom,
yeah. For example, the lowest one on the left is the flow around a rectangular cylinder, which is one of the fundamental geometries that people study.
And even today, people are now beginning to do this accurately.
Right, on computers.
Right. On computers.
Yes.
Right. How about other artists?
Yeah, so the Japanese have always been intrigued by the water environment around them. This is Katsushika Hokusai, a ukiyo-e, or woodblock print artist. And he captured here remarkably what I would consider to say 4 scales of motion in this enormous storm wave. By the way, in the background, that little thing in the background is Mount Fuji. This was actually, and so what you see.
What are the scales?
Yeah, the scales are like the general sweeping motion. That's the largest scale.
Okay.
The second scale is actually the breaking, which you saw in that photograph. The third scale are the little curls.
The little fingers.
The little fingers
that are sticking out.
That's actually his appreciation of vorticity. There's actually vorticity, which we'll come to. And finally, you see the droplets.
Little droplets that come off of that.
Yes.
So the nonlinearities actually produce all of these different scales as energy or something flows from cascades from one scale to the other, and long ago he captured that in his art.
Right.
That's quite amazing.
Yes.
How about other artists?
Well, yeah, Morris Graves, the abstract expressionist, also represented very deep waves, and his breaking obviously was less realistic. It was more abstract, but you can definitely see the large swirling trough and the fingers.
Right. So this was, I guess, 1944. So it's coming up more to modern times and times when you had more abstraction and impressionism occurring in the in the art. Well, Vincent van Gogh also depicted these things. What is this we're seeing?
This is one of his Starry Night pictures, and the reason I included it is not because he was, I don't think, explicitly representing vortex motion. Now, vortex motion is a rotating motion, and what you see here, in my view, in addition to the large objects, roundish objects, are two vortices rotating around each other. This was his way of representing a certain kind of dynamism in the sky. It wasn't a real picture of vortices in the sky.
So it's more a turbulent sky than a starry,
That's
starry
right.
night,
Right.
actually.
Yes, right.
Well, that's very interesting, and I'm sure there are many others. Well, I know that you, along with Martin Kruskal and Gary Dehm, actually discovered something called solitons. Now, can you tell me what are solitons and how did you discover them? Maybe that'll tell us about what modern scientists do.
Okay, that's really a good question. It sort of gets at the beginning of the field. And what happened was that some people at Los Alamos, in particular Fermi and Pastor and Ulam, had done some experiments on a very primitive computer, one of the first computers, and they observed a particular kind of recurrence or coming back of a solution, one of the first numerical simulations, actually. And Kruskal and I tried to explain that. It was sort of like the pressing problem of the late 50s and early 60s. And nobody could do it analytically. So we took an equation, which actually Kruskal derived, but which had been derived previously, and we didn't know about it. It was called the Korteweg-de Vries equation, and it was a partial differential equation, and it happened to also describe shallow water waves. Okay? It was not only, it was like a universal equation. And we solved it on the computer with Gary Dehm, and we made the first animation, actually, of a partial differential equation.
Is an animation we see of a train of these solitons?
That's right. So what happened, we started with a simple sine wave, and what emerges from this sine wave is a bunch of maxima, and these maxima have a very special shape. By the way, the domain...
one train is traveling to the left, and one is traveling to the right, and they just sort of passing through each other.
Passing through each other, right.
Passing in the night without changing, and so...
They are changing slightly, but they preserve their entity when they come apart.
When they come apart, they're just like they pass through each other,
right.
sort of without
Exactly.
seeing each other.
That's what makes them remarkable.
That's what makes them remarkable. So solitons are these waves that somehow refuse to go away. They remain as stable solutions.
That's right.
Right.
They are like actually eigenvalues in a mathematical representation. So
Right.
you can find them as eigenvalues, yeah.
And is this something that people actually see in real life? I vaguely recall this occurring in canals in
Yes, right.
Holland or someplace.
Okay, yeah, actually, we didn't know about this, but we discovered it later as with science. So there was a guy named John Scott Russell,
Okay.
and he was an applied mathematician as a young man, and he was hired to try to streamline barges on the Union Canal in near Edinburgh in Scotland. And in the process, the barges, because they were pulled by donkeys and sort of set into motion rapidly, generated waves. And instead of the waves dissipating, like most people thought they would, they traveled for very long distances, and he followed them on horseback. And then he went to the laboratory and reproduced them there. So he actually discovered them in nature and in the laboratory.
In the laboratory.
But nobody had an explanation for them.
Right. Well, are these the same, are these solitons, is this also what makes up things like tsunami waves?
Yes, right. So a tsunami is called a seismic sea wave. And these are generated usually by large earth movements under the sea, earthquakes of a kind caused like avalanches.
Which produces the original disturbance.
Right. And then they travel long distances.
Across the ocean.
Across the ocean, right.
Right.
And the height of the wave depends on the depth. So if the ocean is very deep, the wave is very small. But as it starts riding up the coast and it becomes shallower and shallower, the wave rises out and it can become so large, eventually it just topples over. It becomes a breaker.
So it's like a breaker, only they're very big breakers
That's
that do
right.
major damage to cities or whatever they happen to strike.
Right.
Right. Oh, that's very interesting. So solitons are actually a very important feature of...
Let me just add that
waves.
it's also they are also being used practically. Some form of optical transmission technology uses the nonlinear aspect of the optical electromagnetic wave.
You're talking about the light signals that are sent down fiber optic.
Yes.
Fiber optic.
Yes.
Tubes. Yeah.
Right. Fiber optic cables.
Fiber optic cables.
Yeah. One of the prominent experimentalists was at Bell Labs. Yeah.
And those are solitons as well. I guess it's because the the material that makes up the optical fiber is nonlinear or something.
Exactly.
that allows you to do this.
That's right.
So they've taken advantage of that. Well,
That's
right. A tremendous application. Now, I know that in order to understand the various properties of waves in simulations and other things, you often take simple geometries. What do various simple geometries, such as flow around a cylinder or some other simple geometry, tell you?
Okay, so flow around a cylinder is a very easy, it's a simple geometry, it's a very easy geometry to do. Here is, for example, an experiment conducted by one of our people, because he's looking about flow around the cylinder, which is at left. And what you see are vortices.
So there's a cylinder at the left, and there's a flow from left to right.
Left to right, yes.
Across that cylinder, and this is the wake, if you will.
That's right. It's the beginning of the wake.
The beginning of the wake. Okay.
Yeah. And that sharp boundary that you see at the top and the bottom near the cylinder is actually a vortex layer.
I see.
Peeling off and then rolling up. You can see that characteristic roll.
Rolling, right.
One direction at the top and the opposite direction at the bottom.
I see.
And the fact that the pattern is very irregular is an indication that it's turbulent, that the motion in the fluid is becoming turbulent.
Right.
And one aspect of that turbulence I want to mention is, you see at the very bottom it says RE equals 3,800. RE is named after Osborne Reynolds, the famous English natural scientist.
What is that's the famous Reynolds number. So
right.
what is the Reynolds number?
The Reynolds number characterizes the flow and the object. So it's a non-dimensional number. Physicists and scientists work with non-dimensional quantities for scaling. So it's the product of the velocity of the flow, the diameter of the object, divided by the viscosity of the fluid.
And what does it tell you? What does Reynolds
And that
number
tells
mean?
you, if it's low, it tells you the flow is going to be laminar, very regular.
Very smooth,
Very
without
smooth.
turbulence.
That's right. And once you pass a transition and it becomes
Some
high,
critical
some critical
Reynolds
number.
number.
Right, depending upon the object, whether it's a cylinder or a rectangle or whatever. And here, for example, is a cinema, which I have, which is not here as a cinema, but it's by one of my colleagues in Japan who did some of the original pioneering calculations. And you can see he has a Reynolds number. It says 1E6. That means 10 to the 6th. That's a
so
large
a million.
number. Yeah, a million.
And Reynolds number of 1,000,000.
Yeah,
So
and you can see that the flow there, as represented by those white particles, is turbulent.
is very turbulent and produces lots of those vortices or eddies.
Right, exactly.
Around it.
Yeah,
Right. Well, I guess we're all familiar with those eddies that occur. I remember seeing them as you paddle a canoe, and you put the oar in the water, and behind it you produce these little eddies that.
Right, exactly. That's like a cylindrical rectangle.
Right.
Cylindrical rectangle. Yeah.
Right. Well, now what happens if you have a heavy fluid flowing over the top of a light fluid in a gravitational field or on the Earth?
Yeah, that's so. We describe these various simple configurations in terms of the people who analyze certain properties of them. So, for example, a heavy fluid over a light fluid in a gravitational field is called a Rayleigh-Taylor instability, after two English scientists, mathematicians, who analyzed them in a linear representation. And what happens is that you get fingers falling from the heavy fluid into the light fluid.
Falls down into the lower and produces this interesting pattern.
Yes, and that's a strong nonlinear development. And then, depending upon the fluid, most of our experience is water and air, but they don't have to be. Depending upon the density ratio, you can get beautiful vortices forming.
Right. So this fingering, I guess I've seen this sort of thing. This kind of thing happens in a waterfall or a faucet or something, where you have the heavy liquid falling, and once it falls so far, then it fingers and it breaks up.
That's right.
In fact, in some sense, that's what was happening to some extent in Hokusai's wave. It was breaking up into fingers as it fell.
Right.
So okay, that's very nice.
So in other words, you see vortices and breaking waves.
Right.
Yeah.
Well, now there's another kind of wave that I've heard about called shock waves. What is a shock wave?
Okay, a shock wave, again, is that other aspect I told you about. It's a very strong, very high energy wave in a medium. For example, in air, where we talked about acoustic waves, a shock wave is an acoustic wave which is so strong that it forms a discontinuity or a near discontinuity of, say, pressure or density. And an aircraft flying faster than the speed of sound will produce these sonic booms.
So a sonic boom is a shock wave.
That's right.
Passing over you, and you hear the boom as it goes past.
You hear the boom, and
right.
it can actually break windows and things like that if it has sufficient energy.
Real discontinuity.
Yeah.
Okay, we've talked about vortices a bit. What can you tell me is a vortex?
Okay, so a vortex in its simplest primitive form is a rotational entity. And the way to think about it is like a tornado.
Tornado or a hurricane, maybe.
Or a hurricane, right, yeah.
Right. Or a bathtub
or a bathtub
drain
vortex, yeah.
Is a vortex.
Is a vortex, right.
Okay, so it's whirling around
It's whirling around because there is some local excitation of a thing called vorticity.
Okay.
The rotation extends further than the thing. Now, for example, in this particular picture, which happens to be flow around a sphere, I'll come back and describe what it is. The vorticity is generated so that you see that large opening behind the sphere.
Right.
That's a quiet region, but the vorticity closes up and starts producing turbulence.
Turbulence.
Yeah.
But now, vortices can actually turn around and close on themselves and make vortex rings, can they not?
Yeah, right. So that's you might say the next level of complexity, actually.
Right.
So a vortex ring is a closed entity in which the vorticity is going around.
It's turning inside out
right.
somehow.
So it's rotating locally, but the whole thing is translating. Now, I happen to have a simple demonstration of that here.
A smoking gun.
A smoking gun, okay, and I'll explain how it works, but let me see if I can make a vortex. Oh, there it is.
Oh, there it is, traveling
There's
just out like
one.
that.
Okay.
Yeah. Okay.
Notice how it breaks up and becomes turbulent.
Turbulent itself, right.
Yes.
Very nice. And that's actually air that is turning around like,
That's right.
like that.
The smoke is just dyeing the air.
Right. And that actually would be being produced anyway, even if you didn't have the smoke, just by the gas particles coming out. But the smoke just makes it visible.
That's right. The smoke is dyeing it. It provides a visualization technique.
Right.
Actually, Murray in the picture of the flow around the sphere showed how he could get quantities to measure, to quantify. He I would consider to be the father of scientific visualization. He was a French scientist and engineer, and he did experiments on people in motion, animals in motion, birds, and finally, at his old age, he went into fluid dynamics.
Oh, great. Okay, finally then, what is turbulence?
Okay, turbulence is a manifestation we all experience. It's an irregular motion of the fluid. Okay.
Is that the same thing as chaotic motion?
That's right, yeah. So some people call it chaotic or stochastic, depends on the word you want to use.
But it's a kind of randomness.
That's right, yes. It's kind of, and so Osborne Reynolds, for whom we named that Reynolds number, actually discovered this. And what he did is you change the Reynolds number, as we talked about. When it's slow and you put a dye in the fluid, the dye just goes off like a thin pencil.
In thin laminar flow.
Right. It just has nothing on it. As you increase the flow velocity in this pipe,
And therefore the Reynolds number.
and therefore the Reynolds number, the little pencil becomes turbulent and diffuses and covers the entire pipe, inside of the pipe.
But it's not just totally random turbulence. I mean, it's something, there's some bit of structure to it. There's energy flow or other things that happen in turbulence,
Okay,
is there?
yeah, that's right. So in turbulent motions, there can be what we call coherent structures. They exist for a certain lifetime, they interact. Now, in this particular picture here, in this animation, you see vortices forming in 2D, and then because of an instability, that 2D array breaks up because of an instability, and you get turbulence. You see that chaotic mixture? On the left is the vorticity, and the right was the stream function. I don't want to get into that. This is an energy spectrum. That means we plot the energy in the flow versus, this is another configuration of...
You plot the energy in the flow versus
the wave number.
Versus the wavelength or the
wave
number, and you see then that there's
And you
energy
see that
flowing
from large wavelength to small wavelength.
small wavelength.
That cascade idea that Hokusai captured.
I see. Well, now these are obviously simulations. How do you do simulations?
Okay. By the way, this was made in 1965, and there's a lot of data on the bottom. And this actually represents these vortices in 2 rows, represents a wake, the von Karman wake, which forms behind the cylinder. So how do you do that? How do you study that? Well, what we do is we take the differential equations.
Take the equations that these mathematicians have produced.
Right. Yeah.
And you actually solve them in the computer or something?
Yeah, what we do is we discretize them. That means we make them discrete, because a digital computer can only deal with discrete objects. And so each field, whether it's a velocity or a density, is actually represented by points on a lattice. And then you set up by proper numerical analysis, and you put it into the computer, and if the computer is big enough, you can do a realistic problem.
But this takes enormous computing power, I suppose.
Yes, right. So only in the last few years have people been able to study turbulence on the computer, with, say, the last decade. Although I might say that the computer affected the aircraft industry already in the 1970s for design.
And how did it do that? Because then they could simulate the airflow around the wings or something?
That's right, yeah. So previously, before computers, everything was done by building models and putting them in wind tunnels. And very crude estimates, because we couldn't solve the equations. Everything was done by very primitive scaling. When they realized that the computer could solve these problems, they began to develop methods to do the simulation on the computer. And only at the very end, when they got close, they built a model, put it in the wind tunnel, and checked it.
I see. Right. So, but now they can just take the mathematical equations and plug your geometry as some kind of boundary conditions into your equations, and if the computer is big enough, you can just run away with it, and it will tell you what, in fact, is going to happen.
Yes, in great detail.
Right.
Still, for simple configurations. I mean, if you consider, for example, combustion, where things are burning or changing.
Very complicated.
That's still a little bit
And
further.
weather prediction.
Weather,
I
yes.
mean, weather is one of the, well, von Neumann, I guess, invented the computer in some sense because he wanted to predict weather. Or
Right.
at least that was one of his major goals. And that's very difficult because, as we all know, very complicated conditions, and you often don't know all the boundary conditions.
And the initial conditions.
And the initial condition. So that's a very a useful but difficult thing. So it takes some of the biggest computers that we have today.
Right.
So I guess you probably have a very large computer.
Well, we have access.
You have access to
Yeah,
large
the
computers.
NSF supports many computer
So you
centers.
support major computer centers around the country. Of course, you can do that these days remotely, so that works very well.
Right.
Okay, well, that sounds very interesting. So you and your students do this? You have students working on these kinds of things?
Yes, I do. I've had students for many years since coming to Rutgers.
Okay.
Also some of my colleagues. I'm not the only one.
Right. Well, this has been very interesting, Norman. We're delighted that you joined us today, and we're delighted that you could join us on Science Edition today. I'm Paul Leath. Let's see you next time on By the Book, Science Edition.